Well, good afternoon. It's 12:18. I was 3 minutes late getting, well, 2 minutes, but just turned over another minute. 2 minutes late getting up here, but the trouble is there's nobody in the room. This is supposed to be Cal 3, Math 227, and but like I said, I'm the only one in the room, so I guess I'll go on and get started. Now it's awfully dark outside. I mean, not very bright outside, so I'm having trouble reading. I'm going to go turn on the light for just a minute. Hold on. All right. This is unusual because usually there's 2 students in here, sometimes before I am, and right now there's no students here. So let's go on and get started from the current slide. When someone comes in, we'll go over announcements, but I don't see any reason to make announcements to an empty room. So we were talking about in Chapter 13, functions of several variables. 13.4 is differentials, and we're just about to get started on page 906, approximation by differentials. Okay, we had done some of the leading up to this last time, and we had just done theorem 13.4, which is at the bottom of page 905, and that said that we can choose an x plus delta x, y plus delta x close enough to xy to make the epsilon 1 delta x and the epsilon 2 delta y insignificant. In other words, for small delta x's and delta y's, you can use the approximation. Oh, I'm sorry. Here it is written here. You can use the approximation delta z is approximately equal to dz. Okay? The actual change of z will be approximately equal to your dz. Now, here is the graphic for that, and I find the graphic a little, it's okay, but it does seem to be a little unusual. Let me see if we can fill in the gaps a little bit here. All right, here's your point. I'm going to get my pen set up. Okay, here's your point xy. Okay, and we're going to change the x a little bit. This actually looks like a negative delta x there. That's okay. Same y. And then when you come over here, it looks like you've changed for a positive delta y. Now, frankly, this says if you make the xy close enough to x plus delta x, y plus delta y, these aren't very close, okay? They've exaggerated so they can see them better, I guess. But you see the y value is actually less than the delta y value. So those aren't super close at all. All right, now here is your point xy, f of xy, okay, up here. And there, the 2 points coincide. The plane and the curve itself. They coincide there. Okay, here's x plus delta x, y. Haven't changed y any, but you change that. So if you come up here, this basically gives you what happens with the change of x when y is left constant. So this is similar to your partial of f with respect to x, because you've let the y stay constant. So from here to here, that's approximately that. Now, then you move from x plus delta xy to x plus delta x, y plus delta y. Oh, I'm sorry. This is the let me take this line out again. trying to draw indicate the gradient, not the gradient, the slope, but this is a point on the curve x plus delta x y. That's on the surface, okay? But your x plus delta x y on the plane, which this is, that's up here then, okay? So you see you've got some separation there. And this is what I was talking about. Here's your partial of z with oops. My pen was supposed to be back. There it is. This is your partial of z with respect to x times your delta x. Okay, I think we have a student coming in. Let's hope so anyway. Yes, here he is. All right. What's that?
Just couldn't get out of it. I was like, what I did.
Ha!
Look around. And you left that.
All right, Bill's here. So let me turn things on a bit here and around a bit. Turn on the projector and flip the lights. The projector will be coming on soon. All right, I'll go on and make announcements now since I didn't do any with nobody in the room. I haven't seen anything opened up yet for making midterm progress reports, so I'm going to hold off on those till I see something. It'll probably be Friday before they remember. Another thing on the administrative calendar, which to me is not a big deal, but I guess to some people it is, the Miss Lawson State coronation is coming up tomorrow evening. And it happens to be just next door to us here in the Bessemer Civic Center. That'll be at 7 o'clock, and so you, if you're interested in going to that, I won't be there because I'm teaching a class until 7:45. Okay. I can't read some of these because they print in black and then highlight with a dark blue. It makes it almost impossible. I don't think it's anything to do with me, though. Okay? Now, this isn't anything probably to do with either of you, but I did want to announce it. There may be somebody in the class that's interested. Next Tuesday, I guess I could wait till then. Well, I think it's good to go on and say. Next Tuesday marks the point where they call the 60% completion date for Title IV funds. Now, what that means, or at least the way I understand it, if anyone's on any type of federal financial aid, I think that's what Title IV funds are. Maybe it's just Pell Grant, I don't know, but we count any federal financial aid. Then you have to, if someone is going to withdraw from a class and they got paid by that program to be in the class, if they didn't make it to 60% completion date, they owe the money back, okay? After 60% completion date, which is next Tuesday, you don't owe the money back. So if anyone is thinking of withdrawing, I don't think either of you are, I doubt if the third student is, but if they are, if you're on federal financial aid, it's a good idea to wait till after next Tuesday to withdraw, okay? And that's most of what I see that is of any importance there. Now, this is the volleyball schedule. The Friday and Saturday of this month, this week, Friday and Saturday of this week, October 18th and 19th, is the Gadsden State Tournament in Gadsden, Alabama. So if you happen to be driving by Gadsden sometime Friday or Saturday, find the college, go to it, and cheer our team on the week. Okay. The rest was next week. And then the NASA's Community College Aerospace Scholars Program is accepting applications through today. Today is the deadline, so you won't hear me announce this one anymore. It will be over with. Okay. So, where I was before you came in was on this first slide where we left off last time on page 906. We're doing approximations by differentials. Now, the previous theorem that we did right at the end of the class last time tells you that if you choose your x plus delta x and y plus delta y close enough to xy, in other words, that your delta x and your delta y's are small enough, that would then potentially make your epsilon delta x and your epsilon delta y very small. Okay, if epsilons are pretty small and you choose your delta x and delta y small, then this could be insignificant. In other words, for very small enough delta x's and delta y's, you could use the approximation that your delta z, which is the actual difference in z's, is approximately equal to your dz, which is your differential z. Okay? And that approximation is illustrated graphically here in what I consider probably, it's an okay graphic, but it just has so many lines in it, it's almost hard to follow. Okay? Here is your original point, xy. Here is f of xy, which is on both the surface, which is the tan kind of colored thing, and the plane that is approximating that surface, and that's from your differential. Okay? And I drew this line here because you're going here from xy to x plus delta x, y. In other words, you kept the y constant, but added a delta x. In this case, actually subtracted delta x, as appears to be negative here. Okay? Which is fine. Perfectly okay to do. And the x plus delta xy, when you do the f of x plus delta xy, that puts you on the surface up here, but your approximation puts you up here on this corner of that blue plane. And this line here that I just did represents the partial of z, which is your function here, your f function. I've been calling it f, they call it z. Partial of z with respect to x times your delta x. The delta x is this length here, and this is your slope of that, the partial of z with respect to x, times this, that gives you that segment right there. Okay. Now, here's your x plus delta xy, and here you're going to x plus delta x, y plus delta y. So this distance here, which looks like a pretty significant distance there, is your delta y. This is your delta x distance, which looks big enough to be too, but this is really a big delta y, bigger than y value was to begin with, you know, so it's a pretty good size. So these aren't small delta x's and delta y's, but I think they did it just so you can see what's going on. So if you've come to here from this point, now you have a gradient, I don't want to use that term yet. You're changing y but keeping your x constant. So this is the partial of f of z with respect to y at the point when x is equal to x plus delta x. So that doesn't have a particularly valid thing. That's not the partial of z with respect to x or y. It's something a little different altogether. So that would be the slope here. That's represented. The partial of z with respect to y would be that slope there, at least taken from this point. Okay? So I would put a bar here and say at x plus delta xy, okay, from that point, and then multiply that by your delta y here, and that gives you that one there, that representation. Now, this is the actual value of your surface at x plus delta x, y plus delta y. Okay, so this difference between this value and this is where this I think is at fault. Okay.
Question.
Yes.
You see the point XY?
Right here.
Right here. Now go straight up.
Got it.
Okay, now go inward.
That one.
What's that point right there?
This one. That's a good question. That may be where they're talking about here. Let me see.
I'm trying to picture my mind the same as
Yeah.
distance. We're doing a three-dimensional distance.
Right. I'm trying to see what that would represent. Because this is your z at x plus delta xy is up here. I think this just happens to coalesce at the same point, but I don't think it had anything to do with this. Now, here's what. I don't know. The picture kind of drives me nuts, okay? Okay, I think I've got what it is, and I think it's okay. Maybe everything is just like it should be here. You projected this point back to this plane. I think that's what that is. Because that then puts it here, so you can call, because I look at this and say, no, the delta z is between here and here, you know. But this is on the same plane as that. So when you project this back to here, so you're on this plane here, the plane that has this, then that's the point. So that is a key point, and that's exactly what it is. It's where this point is projected back onto this plane. So this then makes this the delta z, and this makes it the dz here. And that was one of the things that was bugging the fool out of me, because I said, it should be going from this point, but your question brought it out. This point is just a projection of this back to here. So now you're on the plane, so you can make that comparison, the dz and the delta z. Because you see, they both went from here, and it seems like they should have made a bigger deal about what that point was. But I think that's exactly it. That's this point projected back here, so that you are now doing your, that is where your z value on this plane is the same as the z value on this plane. That's the same because nothing's changed there. But now you can compare this z to that z. I'm sorry, this. Yeah. This z to that z, and this z to that z. Yeah. And this is your dz. I think. Okay. I'm glad you asked that question because I was saying, they've got something wrong here, okay? But I think they do have it right. It's just a projection back onto that plane. Now, I drew this in initially just to show you that is your, that's what we've been looking at, partial z with respect to x, delta x. That is what we're looking at, but it's really not helpful in this picture, so I'm going to take it off. Right. So, yeah, you're right. This point here, which they should have done something to say this is important, that's the projection of this back onto here. Now you can compare the difference here, there. You see, this is projection up to here, to there, and this is already projection. Yeah, you have to project that then over here and do delta z here, and dz there. Now, your actual change, your delta Z1 is from this place, from your initial point to where this value is. That's your delta Z1. And then when you go from y to y plus delta y, this this is your, here is y, and here is y plus delta y. This is y, and then when you make that, that's your delta Z2. So they do look fairly small. The delta z's are fairly small, not huge, but fairly small. Delta x's and delta y's are pretty big, okay? But your dz's, which is your, and again, we go from this point, which is your xy, to x plus delta x. So this part right here, like I had before, this is here is your partial z with respect to x delta x, which kind of is expressing what you're doing with the delta z1 here, okay? This is, of course, taller than that, okay? And then this part here is when you're just changing the y value, you go from here to there, so that's your partial z with respect to y delta y. That's that distance. This one's this distance, and then this is that distance, and then those two added together gives you dz. That's your differential in z. That's the actual change in z. Not a particularly easy figure, okay, especially to figure. Need it any longer, or are you okay?
No, I was just looking at it again.
Right. Okay. Now, the partial derivatives, partial z with respect to x and partial z with respect to y, can be interpreted as the slopes of the surfaces in the x and y directions. And that is really what I was talking about here. This is that slope of this, partial z with respect to x, and then this is the slope, partial z with respect to y, okay? At a different point, but it's still that partial, okay? That's that slope. Then when you multiply this by the delta x, that gives you this amount, and when you multiply this by the delta y, that gives you that amount. Vertical, whereas the slope has the vertical and horizontal component. That's the vertical component alone, okay? That means that dz, the differential in z, is partial z with respect to x delta x plus partial z with respect to y delta y, which you saw by adding these two. This is partial z with respect to x delta x, that's partial z with respect to y delta y. Add those two together, that gives you your dz. So that's where that equation comes from. That represents the change in height of the plane that is tangent to the point at x, y, f of x, y. That's why I kept calling it a plane. It looked like a plane, it was a plane. Because the plane in space is represented by a linear equation in variables x, y, and z, the approximation of delta z by dz is called the linear approximation. So certainly delta z is the actual change of z, and dz is the linear approximation of that change of z. And you saw ours overshot quite a bit. So let's do example 3. And by the way, example 3 is at larsoncalculus.com. You can see an interactive version of that type of an example. Use the differential dz to approximate the change in z is equal to square root of 4 minus x squared minus y squared as x moves from the point 1, 1 to the point 1.01 and 0.97. Compare that approximation with the exact change in z, which is your delta z. So, we're going to use the differential first. So what is dz, according to what we were just saying? Partial of z with respect to x times your delta x plus the partial of z with respect to y times your delta y. Yeah, that's it. So, two things we got to do, well, several things we got to do. Let's first do the partial of z with respect to x. Now, before I do that, I'm going to rewrite my z. I'm going to write it as 4 minus x squared minus y squared to the 1/2 power. I just prefer taking derivatives of that to that of a radical. Okay, I don't like taking derivatives of a radical. So what would the partial of z with respect to x be? 1/2 whole quantity 4 minus x squared minus z y squared to the what power though? What power is this raised to?
Oh, that's right. Minus 1/2.
Minus 1/2 power times
2x.
Minus 2x.
Minus 2x.
Okay, got it. All right. Now this 2 is going to wipe out that 2 there. Okay. So what we have here is I'm going to write it back in radical form. Okay. Minus an x over the square root of 4 minus x squared minus y squared. Okay. That's your partial with respect to x. Okay. Somewhere we need to do the partial of z with respect to y. And I think you can say it's going to be very similar, minus y over the square root of 4 minus x squared minus y squared.
Okay, you got minus. Here we go. Do dy.
Or the delta. Okay. What is your delta x? How does that change from here? Second? It's just a...
Minus 2y.
No, okay, wait. The delta x here, the change of x from here to there, okay, that's going to be 0.01. That's how much x changed from 1 to there, okay? And your delta y, it changed from 1 to 0.097, so what would that be? A negative 0.003, because it's in the negative. It went from 1 to that, so it went negative. All right. Now, we need to evaluate these, and that's the sort of the tricky part. We evaluate them at the original point, 1, 1. So let's do, and that's the one thing they did leave out on the other one, I'll see if I can get it written up here. Partial of z with respect to x at 1, 1. And there was the value that would be a minus 1 over the square root of
Is that 2?
2, square root of 2. Okay? Minus 1 over root 2, and I think you'll find this is the same thing. Minus 1 over root 2, just because the values are the same. Okay. That's your, now, so let's approximate what the dz is, and that would be this. Okay. All right, I gotta find that again. There it is. partial z with respect to x at 1, 1 would be minus 1 over root 2 times 0.01 plus a minus 1 over root 2 times a minus 0.03. All right. Now, you could just pull out the minus 1 over root 2, and then you have a minus 0. No, you already pulled that out. A 0.01 minus 0.03. Okay, so this would be minus 1 over root 2 times minus 0.02. Now I'm sure you can write that in some neater way, but that's how they do it. Wait, okay, and a minus and a minus, that'll make it plus. Okay, sorry, forgot to do that. And you can either plug that in a calculator or, as they did, which is rather strange, rewrite this as square root of 2 over 2, which is what 1 over root 2 is, times 0.02, and this 2 will cancel and make this a 0.01. So root 2 is 1.414. So this will be 1.414. Okay. Is that what they, no, 0.01, sorry. You still have a 0 in there. Okay. Is that right? Yeah, that's right. Okay. All right. Now, it says compare that approximation with the exact change in z. Well, the only way you can get the exact change of z is to evaluate z at 1.01, 0.97, and that would be the square root of 4 minus 1.01 squared minus a 0.97 squared. I don't have a calculator, do you? I don't have one with me anyway. I could pull up one, but then I'd lose my screen, I think. You don't have to if you don't want to. We can just look and see what we did in the book. Second. Square root of 4 minus 1.01 squared minus 0.97 squared. Square root of all that. While you're doing that, then you would subtract from that z at 1, 1. Oops. My thing didn't come up soon enough, and that would be the square root of 4 minus, come on, 1 minus 1, which is square root of 2, which I think we had already done, but that's okay. So whatever you get this is subtract square root. Yeah, then subtract square root of 2 from that. That's your actual delta z. The difference there is delta z.
this turns out 0.50658.
Uh-oh. They say 0. Okay. Is that this part? Right.
No, under the radical, you should have 1.9208. You have that? 4 minus.
Oh, this one?
Yeah, 4 minus 1.01 squared.
Right. Minus.
Minus 0.97 squared.
Right.
And this comes up to 1.9208.
Okay. And then subtract from that root 2.
Okay. Minus 1.414.
Right.
0.50658.
I get 0.0137. Now, I don't have a calculator to do it on. Let me see if I can pull one up quickly.
Check this again.
Let's see if I can get my calculator to work. Okay. Now this has a different syntax, I'm pretty sure, from yours. So that would be 4 minus 1.01, 1.01 squared minus 0.97 squared equal, and then take a square root of that, which is here, and then subtract from that the square root of 2. And I got the same thing they did, 0.10137.
I'll go back and see what I did.
Okay. Now, so that's what they came up with, and unfortunately it's erased everything we just did. Yuck. I knew it was going, or I feared that it was going to do that. Okay. But the delta z we had before, let me get my pen back. Remember that was 0.01 times 1.414, so that was 0.01414. And your dz, which we just did, was 0.0137. Yeah. Okay, so the difference is 0.0004. Okay, so it's pretty small. So that's how we did it. Let's just see how they did. Okay? The x, y is 1, 1, and the x plus delta x, y plus delta y is 1.01.97. So your dx, which is your delta x, is 0.01. And your dy, which is also your delta y, is negative 0.03. I think we got both of those right. So the change of z can be approximated by your approximate is the dz, which is partial of z with respect to x dx, plus partial of z with respect to y dy. I can't recall if.
We didn't do that, but
What's that?
You had originally put that up here.
Yeah.
Yeah.
Yeah. And we did the calculation. Yeah. This is what we're doing. This is your partial with respect to z with respect to x, and that was with respect to y, and this your delta x and delta y. And this was a minus 1 over root 2, and this was a 0.01, and that was a minus 1 over root 2, minus 0.03. Okay, yeah, and that's what we got. So your delta z, which we're using to approximate dz, is minus 1 over root 2 times 0.01 minus 1 over root 2 times a minus 0.03, which came up 0.02 over root 2. And that's why they did it. They're going to use a calculator anyway, but they did root 2. This is root 2 over 2. So flip that over. This is
Well, you still get the same answer.
yeah, and you get the same answer.
You don't get 0,
Yeah.
1, 4, 1, 4.
Yeah, that's exactly what we got. And here is a picture of that. In this figure, you can see the exact change corresponds to the difference in the heights of the 2 points on the surface of the hemisphere. Okay? See if I can figure out what they're saying here. This is a hemisphere. It's only a positive. And this would be, if you squared both sides of this, you get z squared is equal to 4 minus x squared minus y squared. Add those here, and you get x squared plus y squared plus z squared is equal to 4, or 2 squared, so this would be a sphere of radius 2. Okay. This is nowhere close to an easy figure to look at, okay? So the first point is 1, 1. So it's somewhere in there, okay? And the next point is 1.01, which is slightly past that, and 0.97, which is slightly to the left of that one. And this is where you see them better. This is 1, 1, and this is 1.01 minus, or 0.97. So this is the second, this is the original, okay? So this projects up. And you see, you're supposed to see that's 2 dots. It's not obviously, it's obvious it's 2 dots, okay? This dot is a little bit shorter than that dot, the difference being what we just determined, 0.004004, something like that, okay? The difference is given by delta z, which is the actual difference. F of 1.01 minus f of 0.97 minus f of 1.01, that's your x value, y value 0.97, minus f of 1.1. And when you do that, that's what you get. They don't show all the work, but this is the thing we were trying to calculate, and this is minus root 2. And that difference is that, okay? That's the differential form. No, I'm sorry. That's the actual value. The actual value. The previous was the differential value. Okay. Okay. Now they say at the bottom of this page, page 906, a function of 3 variables, 3 independent variables, w is equal to f of x, y, z, is differentiable at x, y, and z, provided that, it's differential there, provided that the change of w is f of x plus delta x, y plus delta y, z plus delta z, minus the value at the original point, alpha of x, y, z. And that can be written as, provided that thing, the difference there can be written as this, delta w is partial of x with respect to partial of f with respect to x times your delta x plus partial of y with respect to partial of f with respect to y delta y plus partial of f with respect to z times delta z. And then you have three epsilons. An epsilon for your delta x's, an epsilon 2 for your delta y's, and an epsilon 3 for your delta z, where these three will approach 0 as the delta x, delta y, and delta z are approaching 0, 0, 0. In other words, when these are getting closer to that, and this is getting closer to that, this is getting closer to that, then if this works out, then that's got to be that. With that definition, differentiability, theorem 13.4 has the following extension for functions of three variables. If f is a function of x, y, and z, where f sub x, f sub y, and f sub z are continuous, and an open region R, then f is differentiable on R. You can write it. Yeah.
Do those deltas have to go to 0 all at the same time?
Not at the same rate, if that's what you're saying, but certainly as the points get closer together and those delta z's are getting closer to 0, it could be that one of them's getting there faster than the other two, but they all have to be approaching 0. It's just like our tangent line used to be. The secant line got closer and closer to the tangent line as the delta x gets closer and closer there. So this is just all three of them are getting closer. And again, because they may have different shapes in different directions, one may be approaching a little bit faster than the other just because it was a steeper to begin with.
I just want to make sure that delta x didn't have to be equal to delta y.
No. Yeah, I would think not. It just wouldn't make sense if they did, unless it happened to be very uniform shape that, and you were right at a point where everything was interacting the same. Okay. Okay. As is true for a function of a single variable, when a function on two or more variables is differentiable at a point, it's also continuous there. Okay, if it's differentiable there, it's got to be continuous there. Just because it's tenuous there doesn't mean it's differentiable there, but if it is differentiable, it's got to be continuous. So differentiability implies continuity. If a function of x and y, or x, y, and z, or as many as you want to, is differentiable at x0, y0, then it has to be continuous there. Otherwise, it has to be.
With something like the cusp.
Yeah, it could. Yeah, that's why continuity doesn't imply that, because the cusp is continuous but not differentiable there. But if it's differentiable there, it's got to be continuous. You can't have any kind of break in the action there if it's differentiable with those partial being continuous. If they're continuous, that means the function has to be. So here is a function. This is example 5. We skipped over example 4. In fact, I skipped over it because I should have done it. So let's go back. I guess we'll do it here. It's not a great place. It's an error analysis problem, example 4. I need more white space. I'll use this one. Okay, that's more white space. Okay. The possible error involved in measuring each dimension of a rectangular box is plus or minus 1/10 of a millimeter. Okay? And I want to go on and name those. I want to call them the epsilons, but I don't know if that's fair to do so. Okay. The dimensions of the box are x is equal to 50 centimeters, y is equal to 20 centimeters, and z is equal to 15 centimeters. Okay. Now, my picture's not going to be as good as theirs because I don't draw these things well. They put the base of the box on the YZ axis and the edge of the box along the x-axis, okay? And keep the box positive, okay? So they have the x, say 1, 2, 3, 4, 5. We'll do this to here. Y is 1, 2, 1, 2. So I'm going to connect those 2 points and these two. Okay, and z is 15 centimeters. 1, 2, so it comes to right here. So it comes down here, 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 something like that. Mine's not as pretty as theirs. Okay, sorry about that. So this is 50 centimeters. That's supposed to be a square there. Mine doesn't look very square. Okay. 20 centimeters. And this will be 50. Oh, it's not a square. It's 15 centimeters. I'm sorry. So it's not a square. I feel better about it now. Okay. Use dV to estimate the propagated error and the relative error in the calculated volume of the box. So they've told you everything kind of backwards. You first got to calculate the volume of the box, okay? And then we'll talk about the error. Oh, you don't have to, but the dV is equal to partial of v with respect to x dx plus partial of v with respect to y dy plus the partial of v with respect to z dz. Okay, that's ugly. I was trying to fit it in here, but not doing a good job. dz. Okay. So, as I said, first thing you got to do is the volume of the box. What's the volume of the box? X times y times z. Okay? Well, so the partial of v with respect to x would be help me. My head hurts.
Do we have to do the partial?
Yeah, it's yz times, goodness my head, delta x plus xz delta y plus xy delta z. Okay. Now, I'm sorry, but my head just started hurting. Like it could be a bad one. I hope it won't be. Okay. Now, we know all the what? I'm sorry. This is supposed to be dV. I don't know. I started writing something else, and I just got to changing it. So this is dV. I was going to write down each one of them, but I decided against it. Your dV, I was going to do the partial vector and then plug them in, but we've done it, okay? Oh yeah, I had already written that. What I wanted to do, yeah. That's what my original thing was to be. Sorry. I got to thinking about my headache and not anything else. Okay. Partial V with respect to X was your XY. This is what I was going to do. Partial V with respect to Y is XZ. I already had that stuff down there. And the partial of V with respect to Z is XY. Okay. And we don't need the DZ after it. Oh. Okay. All right. Now the next thing I was going to do, your dx, dy, and dz are all your 0.1 millimeters. But we have a problem, Houston. Okay? And here's what it is. These are all in centimeters, and that's in millimeters. So, that would be 0.01 centimeters. So to keep the units the same, it's better to write this as 0.01 centimeters. Now, unless they made a mistake, yeah, no, that's exactly what they do. So this is your dx equal dy, because they said they all had that same error, plus dz. Now notice those are not the same relative errors, they're just the same absolute errors. They're all off by 0.01 centimeters. Okay. So with that in mind, goodness gracious, I just hit my knee. Well, I hit my ankle, which twisted my knee. And this is the house that Jack built. Okay, your YZ is 20 times 15, which is 300 square centimeters. I don't know if it's worthwhile doing this. Times 0.01 centimeter plus your we probably should be saying plus or minus, but I'm going to leave that off for now and just understand it is plus or minus. Your partial with respect to y is xz, and that is, oh my goodness, this is harder to do. 50 plus 25, 75. Ooh, that's not right. Yeah, 50 times 15, 750, right? Square centimeters times 0.01 centimeter plus xy is 1,000, right? 50 times 20, 10, 0, 0, yeah, 1,000 square centimeters times 0.01, yeah. Okay. Now basically what the 0.01 does is move your decimal 2 places. So this will be 3 cubic centimeters plus 7.5 cubic centimeters plus 10 cubic centimeters. And that would be 10.5 plus 10 is 20.5. Okay, now that's your estimated error in your volume. And I think at this point we can put in the plus or minus, because they could be plus, they could be minus, and they could be in between those. Okay. So that's your dV, okay, plus or minus 20.5 cubic centimeters. All right. Then it says use that dV to estimate the propagated error and the relative error in the calculated volume. Now the propagated error, they don't even mention. Do they?
You probably want to go all the way back to chapter 9.
But in their working out further down the page, they don't even mention it. Do they? Oh, wait, there it is, there it is. And the propagated error is approximately, oh, okay, I'm sorry. It says UdV, okay. Use dV to estimate the propagated error. The propagated error is dV. Sorry. Propagated error is approximately dV, which is, okay. So that is our propagated error. I was just calling it dV. But that's the propagated error. Now, and it says then to estimate the propagated error and the relative error in the calculated volume of the box. Well, your calculated volume was 50 times 20 times 15. Well, 50 times 20 was our 1,000 again. Times 15 would be 1,500, right? Wait. 15,000, yeah. Of course. 1,000 times 15 is 15,000. So your volume is 15,000 cubic centimeters. So your relative error is your estimated error, which is our 20.5 cubic centimeters divided by the 15,000. My screen keeps falling on me. 15,000 cubic centimeters. Okay, so those go, the units go out, and your relative error is just 1%. And I don't have a calculator to do that, but they say in the thing, and they're putting the plus or minus, which is good to do, I'm sure. That is plus or minus 0.0014, which, and if you express it as a percent, would be plus or minus 0.14%, which is pretty small, okay? Yeah, 0.14%. I lost my place there.
Okay, that's a round thing. I was trying to see how that get 1.36. Okay.
Yeah, I just used the number they had in the book. I didn't have anything to calculate it with. All right. Now, then after that, we did this problem. We played around with it, and we did that theorem. We skipped the problem and did the theorem. Here is example 5, which follows that theorem there. All right. for this function, f of xy, keep up with my time here. Yeah. F of xy is equal to, I have to stand up, minus 3xy over x squared plus y squared. Anytime x and y are not equal 0, 0, but when they are equal 0, 0, xy is that, then we're going to define that to be 0. Of course, if they're not, you can't use this for this because that would be 0 in the denominator. Now, the question is this function, I'll show that f sub x exists there, f sub y exists there, but f is not differentiable there. Now, I can almost see why, but they say they both do exist there. So let's do the calculation and see if they do exist there. What is your, let me do the f sub x up here. F sub x, we'll first do it at xy. What would that be?
Partial with respect to,
What's that?
partial f with respect to x plus
Right. And,
with respect to y with,
okay. Yeah, that's what we're doing, but let's actually calculate them. And that is going to require a quotient rule. Yeah.
we'll do partials on all of them, right?
Yeah, we're going to do partial with respect to x and partial with respect to y. Okay, so let's do the partial of f with respect to x first. And that's a quotient rule.
Push the x square plus y square up and give it a negative exponent.
What's that?
We want to take the denominator and
Right.
give it a negative exponent.
Oh, okay, you can do it that way if you want to, sure. Okay, minus 3xy times x squared plus y squared to the minus 1/2. I mean, no, to the minus 1. Okay. Yeah, you can do that if you want to.
Oh, but you want to do it, take the denominator first and then
Yeah.
do the
Ta-
derivative on the
numerator.
On the numerator.
Yeah.
And
I actually prefer it this way, but I just thought, I don't know why I thought you'd rather do a quotient rule. But if you don't like it, I like this way better, okay? It is a little messy at the end. It's cleaner up front, but a little messier at the end. The other one is just messy everywhere.
well, let's do the quotient rule.
Okay, quotient rule is fine. It doesn't matter which one.
Okay, the x squared plus y squared
X squared plus y squared
times, let's do, okay, that'll be 3y.
minus 3y. Okay,
Plus,
minus
oh,
quotient
minus,
rule, yeah.
minus,
Yeah.
That'll be 3xy.
Yeah, but it's a minus 3xy times,
Just x squared, 0, 2y.
yeah,
2y, right?
with respect to x is 2x.
Oh,
We're doing it with respect to x. Right?
that's right. I don't know how I got over the water.
Okay. And then that's all over the denominator squared. Okay. Now, I actually want to flip sides, or reverse the order, because I like to lead off with the pluses. So that would be 6x squared y minus 3x squared y minus 3y cubed. Okay, over that denominator squared. Well, surprisingly here we have something you can subtract. That will give you a 3x squared y minus 3y cubed over x squared plus y squared squared. f sub x at 0, 0, any at xy. And how in the world they say that does exist at 0, 0, it doesn't. Okay? It says you can show that f is not differentiable at 0, 0 by showing that it's not continuous at that point. Of course it's not. To see f is not continuous there, look at the values, blah, blah.
I thought if it were not continuous there, it could be differentiable there.
I'm sorry.
I thought if it was not continuous at that point, xy,
Yeah.
it can't be differentiable at that point.
Right. Well, okay. Yeah. If it's not continuous, it can't be differentiable. Yeah. So.
Well, he's saying it's continuous.
I know.
It's not.
This is not making sense, okay? It says show they exist. In my mind, that doesn't exist. You can't plug in a 0, 0 there. But what they're saying is using some convoluted rule here, f of x.
Is there something to do with f when f is equal to x or y
Yeah.
is equal to x?
At the top he says you can show that f is not differentiable at 0, 0 by blah, blah. And then down the page you say f sub x is equal to 0. Wait a minute, you just said it's not differentiable there, so how can you differentiate it?
You use 13.5, but you just put 13.5 before, say if a function x and y is differentiable,
Yeah.
it's continuous, but you say at the same time, the negative of that, if it's not continuous at that point, then it's not continuous at that point.
Yeah.
That's what
Yeah.
I mean, 13.5.
There must be something okay, and then he says it further down, okay? Okay. The solution, after it says solution, you can show that f is not differentiable at 0, 0 by showing blah, blah. Then it says that when you talk about those two things. So the limit of that does not exist. You can conclude f is not continuous there. Thereby, by theorem 13, you know it's not differentiable there. On the other hand, by the definition of partial derivatives, you have, and they say that it is equal to 0. And so he says the partial derivatives do exist, even though the function is not. Okay, I guess that's what he's saying. Okay. Remember what differentiable means for a two independent variable problem.
We can hold one constant, then
Yeah, and when you do each of them constant, they seem like they're okay, but the whole thing is not differentiable because they're not okay, because it's kind of like this. As he said, when you are coming in one way, your limit is minus 3/2. Coming in the other way, it's plus 3/2. So they're not continuous there. But if you did the partial of this, because that's flat, you get a slope of 0, and this gives you a slope of 0. Those are the partial derivatives, but the total differential doesn't exist. Okay? I guess that's what it's saying here. This is rather bizarre. Okay? Since they have it here, let's see if we can figure out what they're saying here. Let me erase mine. But that's the point. It says show that they both exist, but not differentiable. When I go to take a derivative, a partial derivative, it doesn't exist. I mean, it's not continuous, so it's not differentiable. We know that. Here is the graph of it, which doesn't do a lot for me. It's not continuous at 0, 0, even though the graph looks like it is. I don't know. It doesn't seem like it could possibly be.
I think he's saying let x equal y.
What's that?
I think he's saying let x equal to y.
That what for what?
Let x equal to y.
Right. Yeah, that's what he's saying. You're right. When he says xx, let x equal y, and then they're coming in. And then let x equal minus y. Okay. So one time he's coming in. Here's the xy plane, which is sort of bizarre here. When x is equal to y, you're coming in this way. That gives you the minus 3 halves or whatever right there. When x is equal to minus y, you're coming in this way, and your f of xy is 3 halves up there, not minus 3 halves. Minus 3 halves down here, 3 halves up there. No way those are going to be differentiable there. Now,
That's the only way it comes to the point.
yeah.
That's a case that, like the cusp, it's continuous at that point, but it's not differentiable.
Yeah. It looks like to me, you might say this is an infinite slope here, because it seems like it's one value down here, another value up here, and that you have an infinite slope in between. I don't know. I mean, it's, but I think that's what they're saying, because the partial of f with respect to x, though this if you're coming in this way, partial of f with respect to x is 0. Coming in this way, partial of f with respect to x is 0. Partial of f with respect to y is 0. Partial of f with respect to y is 0. Everything seems to be 0 there, except the values don't ever touch each other. They're skew lines that have the same slope. And that's the only thing I can figure is that here is showing that the limits are different limits there. So the limit doesn't exist. F is not continuous there. It can't have a derivative there. Not meaning it's not differentiable there. The whole function isn't. But the individual partial derivatives, they say, do exist. Now, this is going back to the definition, and which to me seems like a weird thing to do. Of course, this is the reason. Remember, he defined f of 0, 0 to be 0. That wasn't defined. So he defined it that way in a partial. Yeah. And what is this thing? Let's go back to our function, f of delta x 0. Okay? When delta x is not 0, then what you have here is y is 0, this would be 0. So this is, the top is just 0. Down here you get delta x squared plus 0, because y is 0, okay? So that gives you 0, yeah, that gives you 0 over something that's not 0. Okay, I see what he's saying. In a weird way, okay, I see what he's saying. If you let the delta x not be 0, then this would be 0 over something not be 0, because it would be delta x squared plus 0, which is just it's something not 0, okay? But the numerator is 0, so that means your partial of f with respect to, by the definition, that would be a 0 here over a non-zero there, minus this value, 0. That would indicate that the partial there is 0. And then you do the same thing with y. X equals 0, but this is delta y. The numerator is 0. But down here you get a 0 plus delta y squared. When delta y is not 0, that's not 0, but your numerator is. So that would be a 0 minus 0. So it looks like your slopes in both directions are 0. The trouble is they're along different planes or lines. So even though the partials are 0, they don't even connect with each other. Now that's the best way I can see it. Okay. And that's, on the other hand, by definition of the partial derivatives, going back to the definition with the limit, as long as that delta x in the denominator and delta y in the denominator are not 0, just approaching 0, then both of these are 0. Okay? So the partial derivatives do exist, but it's not differentiable. That's what his point is. Just because the partials exist doesn't guarantee it's differentiable. Now, that's by the definition they exist, but if you go back and do the partials like we just did, they don't exist. I mean, that's where I have a problem with his definition. The limit definition is one thing, but when you actually do that partial derivative, you wind up with 0 in the denominator. And that, yeah, I just don't see. That's the part that bugs me. Anyway, we beat that to death, I think. 13.4, homework exercises. Any of the odds 3 through 7, they're all at Calc Chat. 3's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. 11's at Calc View. 15 and 17 are both at Calc Chat. You can explore doing 19, which is just a continuity. I don't know if it's actually, well, I guess there is an answer to it, but it's not numerical. It should be at Calc Chat if you want to look at that answer. And then any of the odds 21 through, wow, 33, they should all be at Calc Chat. And there's a whole variety there. Areas, volumes, numerical analysis, wind chill, resistance, power, acceleration, volume, sports, inductance, and pendula. Okay, so a whole variety of problems there. I do the ones that you're most interested in, the odd ones. Then you could do 35 or 37. They're both at Calc Chat. 35 is at Calc View, and 39 is at both Calc Chat and Calc View. All right. All right, let's move on to, we don't have much time, but we have a little bit. 42 and we go to 55, so we got about 13 minutes. So let's go to 13.5. Now this can seem a little confusing, but really taken step at a time, it kind of makes sense, okay? Somehow the chain rules, to me, makes pretty good sense. So 13.5 is chain rules for functions of several variables. Notice chain rules, okay? for functions. We'll use the chain rules for functions of several variables, and we'll find partial derivatives implicitly. Loop. Okay. Starting off with this theorem. Now they just say chain rule, singular. For one independent variable. Oh, we're used to this, aren't we? One independent. This isn't. Okay. Let W be a function of x and y. It looks like two independent variables to me. Except that where f is differentiable function of x and y, yeah, has to be the case. But we want x to be a function of g of t and y to be some other function of t. So ultimately, your independent variable is t, not x and y. Those are intermediate variables, and w is your dependent variable. So that's why I say one independent variable, because t is actually your only independent variable here. When I first looked at this, I said, no, they got two, but I didn't read far enough. Where g and h are differentiable functions of t, then your original w is differentiable function of t. Okay? And because there's only one independent variable, that's a pure derivative. D, not a curly d, but a d. dw dt, but it's equal to curly dw curly dx times dx dt, because that's a function of t alone. Curly dw curly dy dy dt. Okay? The chain rule is shown schematically here. Okay? You got one variable, independent variable. Two, what I call intermediate variables. These are both derivatives, they have derivatives with respect to t, because they're functions of t. But because these are both variables of w, these are partials here. So the total derivative of w with respect to t is the partial of this with respect to x times the derivative of x with respect to t. Notice here it looks like the x's cancel out, you get dw dt, and here it looks like the y's cancel out, you get dw dt. And that's kind of how I go about checking and make sure I'm right with this. But these are partials because those are two variables there. These are whole, complete derivatives because there's only one variable for each of those. So this is when you have one independent variable, but you may have two or more intermediate variables, leading to one dependent variable. Okay. I don't know if they use that terminology, but that's what I use. So let's try it. Okay. Let w equal x squared plus y minus y squared, where x is sine t and y is e to the t. Find dw dt, which is correct, when t is equal to 0. So let me get my pen set up. So what would be dw dt? Partial of w with respect to x times dx dt. That gives you partial w or dw dt. But then you have the second part, which is
curly dw.
Okay, curly dw.
Curly dy.
Okay.
And straight dx, dy dt.
dy dt. Okay.
Do you want to start on the inside first?
Okay. Well, we need to calculate both of those and both of these. So let's do it. Curly w with respect to curly x would be what? 2xy.
Minus
Nothing.
0.
Yeah, right. And then curly w with respect to curly y
Be e to the t.
is what?
E to the t.
Well, you got the x squared first, right?
Where are we?
First term?
Oh, first term.
Yeah.
Okay. I'm going to do w with respect to y, right?
Yeah, with respect to y.
0. say dw with respect
to y.
y, and then with
And that would be, for the first term,
is x squared,
that'd just be x squared
and then
minus
is, just 2y.
minus 2y. That's it. Okay? Now let's do our dx dt. And that would be cosine t. And our dy dt is e to the t. So now with those in place, we can figure out what our dw dt is 2xy cosine t plus
X squared minus 2y
right
times e to the t.
e to the t. But that looks bizarre, doesn't it? Because you have x's, y's, and t's all in that. Whereas the implication here, we want the change of w with respect to time, or t, or whatever the t is. So let's get the x's and y's out of there. Well, we can use those to do that. Okay? So this would be 2, and what's your x?
Where are we now?
Okay, we're figuring out, plugging in for x and y, what x and y are here. So your x is
2 sine t.
sine t, and your y is e to the t, and then you have your cosine t, right?
Okay, that's good.
Huh?
Okay.
Okay. Plus,
Okay. Cosine t squared.
no, it's sine t, your x, yeah,
Original,
yeah.
Sine t squared.
Sine squared t minus 2e to the t times e to the t. All right, now that's a little messy looking. Let's see what we can do with it. I'm going to write this as 2e to the t sine t cosine t plus e to the t sine squared t minus 2e to the 2t. Now, there is one thing you can do to make it a little simpler. And
Well, I'm trying to see.
what's that?
The first one
Yeah.
minus, where did you get the,
This times this? Is that what you mean?
oh yeah, okay, just say the exponents, yeah. Okay.
Yeah, I put the e to the t in front here because when you put it after, it gets confusing of whether that's part of the argument or not. You put it in front, and it's not confusing at all. As confusing. Okay. And the only thing you could do to make this just a little simpler is 2 sine t cosine t happens to be the same as sine of 2t. But I don't know if they do that or not. Let's see if they do. No, they don't. They leave it just like this. 2e to the t sine t cosine t plus e to the t sine squared t minus 2e to the 2t. Yeah, that's what they got. Okay. Now, let me clear this if it's okay, because we're going to show it how they did it, and we're running out of time, so let me just get this shown. By the chain rule for one independent variable, here's what we have, just like you said. dw dt is curly dw, curly dw, curly dx, dx dt plus curly dw, curly dy, dy dt. I'm going to get that down before this is over with. Okay? And then going up there and plugging in, your partial of w with respect to x is 2xy. 2xy, and then the derivative of x with respect to t is cosine t, plus partial of w with respect to y is x squared minus 2y, so that's x squared minus 2y, and the derivative of y with respect to t is e to the t. Okay. Now, that has all three variables all messed up in there, so let's get rid of the intermediate variables and write those in terms of the independent variable t, and you have 2 sine t, I wish they'd left it on the same page, e to the t, cosine t, plus sine squared t minus 2 e to the t times e to the t, exactly what we got, and then pulling the things together that belong together, 2 e to the t, sine t, cosine t, plus, and then distribute the e to the t across e to the t, sine squared t, minus 2 e to the t squared, which is 2 e to the t.
One more thing to do there.
I'm sorry?
I said we got to do one other thing there.
Yeah, they don't do the other thing.
T is when t is 0.
Oh, you're right. I forgot they said that. Find that when t is equal to 0. Okay, so this is, what would you call this? This is dw dt. So dw dt when t is equal to 0 would be
2. This is 2 times 1.
Yep.
And then sine would be a minus.
No, sine of 0 is 0. So that term goes to 0.
Then we got
This term goes to 0. And that leaves you
2, just 2.
minus 2.
Minus 2.
Minus 2. That's it. All that work for nothing with minus 2. Okay.
Well,
That's what.
Can you flip the screen back just for a second?
What? The previous one?
No, instead of that slide, go back to the previous slide.
Yeah. Okay, I'm trying to.
Could we have, no, the other one.
Okay.
No, I was looking at the point there, where we could, yeah, right there.
Yeah.
Could we have put t equals 0 right there? Or no?
Right here.
Yeah, that's what
Yeah.
we did.
Yeah. I wrote it down here, but worked on it up there.
Yeah.
Yeah. I kind of got those crossed up. Well, I just didn't want to write it again. I was out of time.
Okay, that's okay.
Yeah. So I was just looking at that. Say, yeah, we can evaluate that and that, but that goes to 0. We can evaluate that, sure, but that goes to 0. And we evaluate that, oh, you go. So I was just plugging in the t equals 0 up there. Yeah. All right. I hadn't flipped the page. Yeah, do they even do that? Oh, there they did. Okay. All right. What do they show next? Yeah, there's what they get. Now, okay, we'll start next time at the top of page 912. They did do something interesting at the bottom of page 911. I know we're out of time, but here was our original problem. Oh, that's it right there. Okay, if that was the original problem, what you could have done was go back and plug in sine t squared for x squared there, e to the t there, minus e to the 2t, and then take the derivative with respect to t directly. But then you would have had product rules and, variety of things. This has potential for making that a lot easier. Has potential. I'm not saying it always will, but it does. So that's what they're doing at the bottom of the page, saying, yeah, you can get there the same way but then you would have product rule, chain rule, everything all messed up together. And the way we did it, it was fairly straightforward. So we'll begin next time with this. Top of page 912. Okay, we did get a little bit done in this section, so let's see if we got a few homework exercises. There won't be many. I think you can do either 3 or 5. They're both at Calc Chat, and 3's at Calc View. And actually 7 through 11 is exactly doing the same type of thing, except they're all at Calc Chat, 9's at Calc View, but then they say go back and convert it and write W as a function of T alone, and then do your differentiation, see if you get the same thing. So whichever one you want to do. And we'll stop there and pick up the rest of those later. So I guess this is what this is saying too. So we'll pick up on that. All right. Any questions? I know. Sorry. Unfortunately, we ran out of time right at the end, and there were lots of potentials for questions. Okay.